Thank you. Okay. Thank you so much for the invitation. So I will share the screen first. Okay. We put it full screen. Yeah. Okay. So let me just hide this a bit. I will talk about quantum field theories of relativistic Luttinger fermions. So this is the title of my talk, which is also the title of the paper that we wrote in collaboration with my supervisor, Professor Gies, who's here listening, and this ex-master student, Philip, and bachelor student, Johannes. So I will start by telling you, how do I, wait, I can't change the, oh, okay. So I start by telling you something about quantum field theories, which is one of the main differences between quantum field theories and classical field theories is that quantum field theories have the remarkable predictive power regarding their scale of validity. So through the renormalization group, one can see how physical observables change with the energy scale. In particular, some theories can be valid up to arbitrarily high energies. So they can be UV complete. And this can happen through asymptotic freedom, asymptotic safety. And an example of such a theory in 4 dimensions is QCD. So QCD is asymptotically free, and at higher and higher energies, the coupling between quarks and gluons becomes smaller and smaller, and so it allows for perturbative calculations. However, we don't know any theory that is based on pure matter fermionic degrees of freedom, which is also UV complete. And during this talk, I will give you a new ingredient for building such UV complete quantum field theories, which is indeed Luttinger fermions. So first, I will start by telling you what is a Luttinger fermion. And my computer is like about to fly. Luttinger fermions were discovered by Luttinger while looking for the most general form of the Hamiltonian of a semiconductor excitation in a magnetic field. And so this is his seminal paper from 56. And the Hamiltonian for such a excitation looks like this. So we have a double derivative, and we have this Gij matrix, which is a matrix not only in space, but also in the band structure of the material. So the different components of the matrix are related to the different bands of the semiconductor. And nowadays, Luttinger fermions are used in solid-state physics to describe effective models of materials that display quadratic band touching or crossing. That is, materials that don't have a linear dispersion relation between energy and momentum, like in this picture. So they don't have like, they are not described by Dirac cones, but by something like quadratic band touching. So like this. And the Hamiltonian, we have a bunch of faces in my computer. The Hamiltonian looks like this. So again, we have the Gij and the quadratic momentum. And by requiring that the Hamiltonian squared is the proportional to the momentum to the force, so the Hamiltonian square contains only even powers of the momentum, one can arrive at the Clifford algebra satisfied by these matrices Gij, and it looks like this. And here I just list some applications of the Luttinger fermions in condensed matter. But since we are interested in quantum field theories, what has been done for the first time is we generalized Luttinger fermions to the relativistic case. So the kinetic action for relativistic theory of massless Luttinger fermions can be straightforwardly written in this form, where psi will be our Luttinger spinor, and we have a double derivative and this G mu nu matrix. So now the indices are Lorentz indices. And in a moment, I will talk about this Luttinger spinor, but first I will give you the some properties of these G mu nu matrices. So again, by requiring the same property that is as before, so by requiring that the square of the kinetic operator gives you the D'Alembert operator squared, you arrive at the same kind of Clifford algebra where the Kronecker delta from the non-relativistic case are simply replaced by the metric. So these G mu nu matrices are d gamma by d gamma dimensional, where d gamma is the dimension of the Clifford algebra. So first, I should say that they are symmetric in the Lorentz indices, clearly from the action. And they also, we take them to be traceless in the Lorentz indices because the trace part gives an operator that is of Klein-Gordon type, which we neglect. So we will take them to be traceless. And what is the dimension of the Clifford algebra? So for this, we first need to count the number of linearly independent elements that we need to span the matrices. And this is given by this quantity, dE. So we have the off-diagonal elements plus the diagonal elements minus the traceless condition. And the dimension of Clifford algebra satisfied by such matrices will be the gamma, at least the dimension of the irreducible representation, and is this number, so 2 to the power, this floor operation, dE over 2. So in numbers, we have that in 4 spacetime dimensions, the number of linearly independent elements is 9, and the dimension of the Clifford algebra is 16. So this means that the matrices G mu nu will be 16 by 16 matrices, and since they multiply the spinor in the action, so the spinor will have 16 components instead of the 4 components Dirac spinor that we know. So more properties. So how do we write an explicit representation of these G mu nu matrices? First, we notice from the algebra, we can simply look at the G0I element squared, and we see that this is negative, whereas the other elements are all positive. So we can say that the G0Is are anti-unitary and the others are unitary. And we can decide to consider, let's say, a representation of these G mu nu matrices that is given by Euclidean Clifford algebra in this way here. So we write the G mu nu as some coefficient that carries the Lorentz indices times an gamma Dirac gamma matrix that satisfies Euclidean Dirac algebra. And as I said, we need 9 of these gammas, so 9 linear independent gamma matrices to span all the G's. Yeah, so we need 9 gamma matrices. So instead of the Dirac, we have gamma 0, 1, 2, 3. Now we have from, let's say, gamma 1 to gamma 9. However, we need to be careful in the definition of the quantities that we have in the action. In particular, one needs to define in a good way the conjugate spinor. So in the Dirac case, the conjugate spinor psi bar is given by the psi dagger times gamma 0. So actually, the gamma 0 is plays the role of a so-called spin metric, and now we need to find a suitable spin metric for our model. So we define in general the psi bar in this way with the H generic spin metric, and we find some conditions that the spin metric must satisfy, in particular by imposing the kinetic action to be real. We have that the spin metric H must anti-commute with the G0 i's and must commute with all the others. And it turns out that we don't find a solution for this H out of the 9 gamma matrices that we have. So in the 16-dimensional irreducible representation, there is no solution for H. You need to enlarge the number of gamma matrices in order to have a well-defined psi bar. And also the symmetries of the action. So of course we have Lorentz symmetry, and under Lorentz transformation, the G mu news transform as a 2 spinor. And moreover, we want indeed the action to be invariant under spin-based transformations. So the G mu news transform in the under the spin-based group, which is the SL d gamma C group, in such a way here, and the spinors are rotated with the SL d gamma C matrix. And the action is invariant if the spin metric satisfies this property here. And so how do we find this H? We go to the next possible representation. So the next minimal, let's say, reducible representation is the one where the gamma is equal to 32, because we have 9 gamma matrices, then we add a gamma 10, so a new gamma matrix, and then we also add the gamma 11. Both correspond to a d gamma equal to 32. So now the number of gamma matrices in the next possible reducible representation grows from 9 to 11. And this means that the spin-based symmetry will be SL32C. And therefore, the G mu nu matrix will be a 32 by 32 matrix, and the Luttinger spinor psi will be 32 component spinor. And it turns out that now we find the solution for a suitable spin metric, and one solution is given here. So you can write H as gamma 1, gamma 2, gamma 3, gamma 10, and this H is the one that satisfies the good properties that are required. Moreover, also if you here change the gamma 10 with the gamma 11, for example, this also satisfies the requirements, and then also any linear combination of the two. So it turns out that actually we have an infinitely many spin metrics that now work. But once you choose your H, you define the psi bar, and you can go from one representation to the other by using a SL32C transformation. So now that we have all the setup, we can look at quantum field theories. So we can start building some models. First, we should notice that the kinetic term, which goes like G mu nu, d mu d nu, in 4 dimensions, this means that the canonical mass dimension of the fermions is 1. So the quartic self-interactions of the form psi bar psi square then are perturbatively renormalizable. So the coupling is RG marginal, and they are interesting to study. Moreover, we have that since the Clifford algebra is quite large, it turns out that the number of spinor bilinears that you can construct out of these Clifford algebra elements is quite large, which is 1024. And so you have plenty of choices, let's say, for your models. But of course, we, for now, focused on selected channel a few selected channels, let's say. First, the first model that was studied by Holger and his master student is an analog model of the Gross-Neveu model, but with now Luttinger fermions. And the action has a scalar channel and a tensor channel, where the spinor bilinear looks like this, psi bar g mu nu psi. And they studied the one loop beta functions for this action, and this is just the result. It turns out that the tensor channel is dynamically generated by the scalar channel, because in the beta function for the tensor channel, there is a lambda 0 square term. So even if you start with the lambda t equals 0, then there will be the tensor channel will be dynamically generated by the scalar channel. So you can study the flow of the couplings in the lambda t, lambda 0 plane. And they found that there is a large region in this plane where the theory is asymptotically free. So there is a Gaussian fixed point, which is attractive in the UV, for lambda 0 that is positive and lambda t that is sufficiently negative. And this, to our knowledge, is the first example of a UV complete quantum field theory that is based on pure matter fermionic degrees of freedom. So after this has been done, personally, I considered Nambu-Iona-Lasinio model with Luttinger fermions. So this will be a model with a chiral axial symmetry. So now we need first to define what is an axial transformation. And in this case, so in the Dirac case here, we would have the gamma 5. At the gamma 5 will be the now is the gamma 10, because gamma 10 is the element that the Clifford algebra that anticommutes with the G mu nus and with the speed metric, whereas in the Dirac case would have been gamma 5, which anticommutes with the other gamma mu's and with gamma 0. So these are the axial transformations, and the action with such a axial symmetry can be written in this form. So it looks like the one for the Dirac case, where now I have gamma 10 here, and of course the kinetic term is the one we have. And again, if you study the beta function that I computed with the FRG methods, again, it is negative. So the theory is asymptotically free, and then it's UV complete. So this so far what we have done for the self interactions, but also I before doing this, actually I considered the coupling of Luttinger fermions to gauge fields. In particular, I considered an analogy, let's say, with the QED, but with Luttinger fermions. So the action for a QED with Luttinger fermions will look like this. And so now we have a double covariant derivative here and the G mu nus. And I computed the one loop beta function, which can be easily, let's say, computed by employing the one loop effective action. So you compute the log det of your operator that you obtain by integrating out the fermions. And let's say the interesting point here is the spin field coupling that turns out from this operator, which will be the analog of the Pauli term in the Dirac case. So in the Dirac case, you have that the spin field coupling is this Pauli term that looks like sigma mu nu f mu nu. Now, what I have looks like this. So let's say it's known that the Pauli term is the term that and contributes to an enhancement of the paramagnetic contribution to the beta function. And now, since we have a non-trivial, again, spin field coupling, this will enhance the paramagnetic contributions, which with this, I mean, what do I mean with this? Paramagnetic contributions is my colleague is always confused about this. So basically, this comes from electrons in a magnetic background. So non-relativistic electrons, you can compute the magnetic susceptibility. And it turns out that the magnetic susceptibility, the total sign is influenced by, is always given by the sign of the paramagnetic contribution. So in your Hamiltonian, you will have an operator, which is separable, let's say, in a part, which is minimal, and that is of Laplace type. And this contributes to the diamagnetic part, which is the orbital motion of the electrons in the magnetic field. Plus, you have the non-minimal part of the operator, which is the one not of Laplace type, and this contributes to the paramagnetic interactions, which are the basically the alignment of the spin of the electrons with the magnetic field. And as you have this in non-relativistic physics, you can draw an analogy with the beta function in QFT. And it turns out, again, that the sign of the beta function in QFT is always given by the sign of the paramagnetic contributions. That is indeed the contribution that comes from your non-minimal operator that you have here. So here the paramagnetic contribution will be given by the spin field coupling plus the other non-minimal part of the operator. And this indeed contributes to the sign of the beta function. So I can compute the beta function in a constant homogeneous background magnetic field. And at leading order, which is the f² order, the beta function looks like this, and it is positive. So just like in standard QED, the beta function is positive, so we don't have asymptotic freedom. But here I stressed the separation between the paramagnetic contribution and the diamagnetic one. And here actually, so due to this term here that turns out to give indeed a very strong contribution, this is even more enhanced with respect to the QED with Dirac fermions, because in QED with Dirac fermions, you will have something like 1 in the paramagnetic part and 1/3 here, so 3 times larger, whereas now is more than 7 times larger. So yeah, this is something that we noticed, and it's good that we recover this feature. Then one can consider a generalization to non-abelian gauge groups. So we can consider QCD with Luttinger fermions in the case of NC colors. And now the computation is almost the same. It's just a little bit more complicated. You will have in the covariant derivative, you have also these taus, which are the generators of the SU-NC group, and your non-abelian field. However, since we are interested in the one-loop beta function, we can consider let's say a simple background, which is a pseudo-abelian field. So we choose our field to be given by abelian vector potential times unit vector that points in a color space. And with this substitution, we can compute again the beta function, and this is what we found. So the part that comes from the Young-Mills sector is unmodified, it's just the literature result, whereas the part coming from the Luttinger, let's say, quarks is this one. And you can also compute the critical color number for which you have asymptotic freedom. And it turns out that for one single Luttinger flavor, you need this number of colors to have asymptotic freedom. So the beta function is negative if the number of colors is basically 10 times larger than the number of flavors. So for each flavor, you need a SU10 non-abelian gauge group for asymptotic freedom. And this is so far all that we have done for coupling of Luttinger fermions with gauge fields. However, let me tell you some more. So if you now let's forget about gauge groups and let's go back to simple Luttinger Lagrangians. So we take a free Lagrangian but massive with Luttinger fermions, and since this is a higher derivative theory, this theory is affected by the Ostrogradski theorem, and which basically tells you that you will have tachyons, also called ghosts. Indeed, if you look at the equation of motion for the Luttinger field psi, you will get something like p to the 4 minus m to the 4 psi equals 0. So you get tachyons in a massive theory. And this turns out to be the case also for a mass term, where here you put in between the two psis, you put a gamma 10. So both for a mass term of this type or a mass term where you put a gamma 10, you have tachyons. However, we found an interesting feature of theories that have instead a mass term where we put a gamma 11 or a gamma 10 gamma 11. So mass terms of this type here. So a mass squared psi bar gamma 11 psi or mass squared psi bar gamma 10 gamma 11 psi. Actually, we don't have tachyons, but the mass poles are shifted to the complex plane. So we get something like p to the 4 plus m to the 4 psi equals 0. And this is something that is seen in theories where you have confinement. So, for example, in Yang-Mills theory. So we should look into this more, but this is so far interesting feature that we found for our massive theories. And so how could we cure this tachyonic problem? Inspired, let's say, by condensed matter physics, where they have already seen a transition between from Luttinger fermions to Dirac fermions, in the sense they have seen in some kind of material that at a finite temperature there is a phase transition between quadratic band touching and Dirac cones. So inspired already by this, we would like to, let's say, transition from Luttinger fermions to Dirac fermions. And this is also encouraged by something else, which is if you look at the standard model and you count the number of spinor degrees of freedom in one standard model family, you will find precisely the number of components of a Luttinger spinor. Indeed, you will have an up quark, so you have 4 component spinor for 3 colors. Same for the down quark, plus electron, it's 1 4 component spinor, and plus you take Dirac neutrino, so you will have both right and left-handed neutrinos. Then, if you sum all this up, you will get 32. So it looks like a one family of standard model fermions fits by also considering a right-handed neutrino, fits in a Luttinger spinor. So by, let's say, inspired by these two things, we can think of going from Luttinger to Dirac. And to do this, we should break the SL32 spin-based symmetry to the Dirac one, which is SL4C. And this could be done by adding an explicit breaking term in the action, which is of Dirac type, like this, where we will have this operator ID/PD will be sort of Dirac projector, in the sense that it projects the Luttinger components onto the Dirac components. And this hopefully cures the tachyon problem, in the sense that by power counting, you can already see that this term would dominate in the infrared, whereas the Luttinger term would dominate in the UV. So in the infrared, the theory will be tachyonless because the Dirac equation doesn't admit tachyonic solution. So we would like to see this transition here. And I think this was it for everything I wanted to say. No, what time is it? Oh, I went a bit fast. So let me recap. So what did we do? We generalized Luttinger fermions to the relativistic case for the first time, and we used them to build quantum field theories. In particular, we saw that self-interacting quantum field theories built with Luttinger fermions can be asymptotically free. And so we saw first examples of UV-complete quantum field theories that are based only on matter degrees of freedom. And moreover, we had a look at the gauge theories with Luttinger fermions, and we saw, we reproduced the nice feature of them having a strong paramagnetic dominance, and this turns out to give us large gauge groups for asymptotic freedom in the case of QCD, for example, with Luttinger fermions. So what we still have to do, or what we have in mind, is first of all, as I was saying, the transition from Luttinger to Dirac fermions. So by breaking this SL32 symmetry, SL32C symmetry to SL4C via some explicit breaking term, and then actually the problem here is that the construction of a suitable projector is not trivial, because we already saw that naive choices of the projector actually break Lorentz symmetry. So, and we don't want to break Lorentz invariance. So we're still working on this. Moreover, we should look at the implications of the tachyons in the massive theories. Also here, I put another point, which is at some point I was looking at self-interactions, but with the mean field approximation via some Hubbard-Stratonovich transformation. And what I saw is for some self-interacting models, I found something that looks like a inhomogeneous ground state. So this is still an open question that we should tackle at some point. Also, another idea is the investigation of the infrared phenomena, because these theories are okay in UV complete, but in the infrared they become strongly interacting. So we should look at the infrared physics as well. And one next thing that we would like to do as well is the coupling to gravity in the context of asymptotic safety, because the Luttinger fermions can be straightforwardly coupled to gravity with, for example, a term that looks like this, where this is a term that is not present in the Dirac case, because you cannot put something like gamma mu, because you will simply get a Ricci scalar. However, now we can do, or we have this kind of term, and moreover, this term is as a chiral symmetry. And it is again RG marginal. So we will like to add this to the Luttinger kinetic term, and then look at how this parameter behaves basically. And that's it for the talk. Thank you for the attention.
Thank you very much, Marta, for the nice talk. And we do have time for a couple of questions.